This is ELEC 1510 Logic Design, Lecture 8, Video 3 on Verilog HDL, corresponding to textbook section 3.9. An HDL is a hardware description language. This is essentially a programming language that's used to design large and very complex logic circuits. So we've been doing logic circuits using schematics in Quartus, but once those get really complex, you don't really want to be designing those using schematics anymore, especially if you design an entire computer processor. And so we move into HDLs to design them. There are two main HDLs that are used out in the world. Verilog, which is more of the academic hardware description language, Verilog HDL, and then VHDL, which seems like the V would stand for Verilog, but it doesn't. V stands for VHSIC, which is Very High Speed Integrated Circuit, HDL. And VHDL is more complicated and is primarily used in defense industries. So we're not going to cover VHDL here, we're only going to cover Verilog. So if you plan to work in defense, you might use VHDL, but we're not going to cover that here. Something that students typically struggle with when they start to use an HDL is understanding that it's not a sequential language. So something like C or Python or MATLAB, all of these are sequential programming languages, which means that instruction 1 is executed, and then instruction 2 is executed, and then instruction 3 is executed, and so on. That's not how HDLs work. An HDL is basically like drawing a picture of a logic circuit, and every single thing that you draw is operating at the same time. It's not like if you draw a logic circuit that you execute this gate, and then you execute this gate, and then you execute this gate. They all execute at the same time, and that's how HDLs work too. So there's no such thing as a for loop in an HDL. There's no switching statements, anything like that. So HDLs are not sequential languages like C. All right, so we're going to start out with very basic Verilog modules. Some of the keywords that you'll be using right away represent what you would see in a very typical logic circuit. So it's pretty much a one-to-one relationship between the drawing of the logic circuit and the keywords that you'll see in Verilog. Modules refer to the circuit in its entirety. So this would be called a module. We have to define modules as being circuit blocks. End module as a keyword tells you when you're done defining that circuit so that you can differentiate different modules from each other. Inputs here are the inputs to the module, the circuit or the module. Outputs are the outputs from the module here. So in this case, we have input A, B, and C, and outputs D and E. Wires are connections that exist entirely within the module. So they're not inputs or outputs. There's only one wire inside this module, and that's right here, because neither end of this wire connects outside of the module. Every single other wire, like, let me draw in the correct color. This wire is an output, this wire is an output, and then the rest of them are inputs. So anytime you have a wire in a circuit that is entirely contained within the module, we call that a wire rather than an input or an output. And then the keywords for gates and, or, and not just represent the gates that we are typically used to seeing. And gates, or gates, and not gates or inverters. So here's an example of a gate-level Verilog module. So we're going to differentiate between gate-level Verilog modules and Boolean Verilog modules. Sometimes I will ask you to write gate-level Verilog modules, and sometimes I will ask you to write Boolean Verilog modules. This is an example gate-level Verilog module. We want to implement the function z equals x and y. So that would correspond to a simple AND gate with inputs x and y and output z. Now here is the Verilog implementation. I'm going to define a module, and I will call it my AND circuit. You can sort of call that whatever you want. Typically, for the main module in your implementation, if you have more than one module, this will be called the top-level design entity, which most of the time at this level in Quartus is the same as the name of your project. And then we write our inputs and outputs, so x, y, z. So it's kind of like defining a function in a different programming language where you have arguments x, y, and z. Then we define our output as being z, so we have a single output z. We define our inputs as being x and y, so x comma y. And you need a semicolon at the end of all of these lines. And then we define an AND function, so AND of G1. So G1 is the gate instance, so that means that we are naming this gate G1. And every gate in your circuit needs its own identifying name. So we're just calling that G1 for gate 1. And then we say what the output is first, so output. And then we tell it the inputs. Then semicolon, and then end module. So we're done. We have defined this logic circuit. All right, that one's pretty simple. So let's move on to a more complicated example. F of x, y, and z is equal to x prime y, or y prime z, or xz. So let's first draw this. This is a sum of products expression. So we're going to have an OR gate, which leads to the output, F. An AND gate here with inputs x prime and y, which is input to the OR gate. Another AND gate with inputs y prime and z. And another AND gate with inputs x and z. Okay, so let's go through and first we'll assign a name to each one of these gates. So I'll call this gate 1, gate 2, gate 3, and gate 4 for the OR gate. You don't always have to draw this every single time, but it helps at first just to visualize what you actually need. And then let's assign wire names to the wires. So we have wire 1, wire 2, and wire 3. Again, wires are internal connections inside the module that are neither inputs nor outputs. Okay, so now in the Verilog, we can actually go through and say what all of these lines have to be. The only output in the whole module is F. Again, the module looks like this. So the only output is F. The inputs are X, Y, and Z. And then we want to define wires W1, W2, and W3. Our first AND gate we have named G1, and the output of that AND gate is wire 1, which we list first. Then the next input is not X, and so how you write the complement of a variable is put an exclamation point in front of the variable, so not X, and then Y, semicolon. Next we want to define gate number 2, which has output wire 2, and inputs not Y and Z. And then gate 3 is an AND function again with output wire 3 and inputs X and Z. Finally, gate 4 is an OR gate with output F and inputs wire 1, wire 2, wire 3. And now we have fully defined that module representing the logic equation. Okay, so sometimes if you have lots and lots of complicated logic expressions, it can be easier to write all of those in terms of Boolean expressions rather than gate-level Verilog declarations. So the Boolean operations that we're going to use at this level in Verilog are a not expression, which I've already talked about. That's an exclamation point in front of the variable. The OR operation, which is a double vertical line. That's the same as in a lot of programming languages. And the AND expression, which is a double ampersand. That's also the same as in a lot of programming languages. So not is like an inverter. OR is like, an OR gate. OR is like an OR gate. And double ampersand is like an AND gate. So let's now implement this same expression from the previous slide using a Boolean expression rather than a gate-level expression. So now we use the keyword assign rather than and or something like that to assign f to be equal to, the first expression is opposite of x. I'm going to put that in parentheses, and so double ampersand y. We'll put all of this in parentheses, or not y and z, or x and z. So now we have designed the same module, but now using a Boolean expression and an assign keyword rather than at the gate level. So either of those are equivalent. You need to know how to do both of them for this course.